Welcome, ladies and gentlemen, to our lesson plan on weight and balance. And so weight and balance is what we're going to be talking about. And weight and balance is incredibly important because one, we need to know how to calculate weight and balance for our aircraft. And we need to know that weight and balance in particular to calculate things such as performance, right? When it comes to the aircraft for takeoff and landing distances, as well as make sure that our weight and balance is within certain tolerances that the manufacturer prescribes, and of course make sure that we understand the effects of weight imbalance and so forth, which we'll talk about. But first we'll kind of look at a little case study of a tragic accident that happened.
Truck time is on at the big Chevy store in Frisco.
So we'll skip that and we'll just actually go over here. There we go. Gotta love ads. Alright, so as you can see here, this is back in 2013 at a military airfield. You see that 747 is climbing, and all of a sudden they're kind of slowing down, and that's because they stalled. And unfortunately that stall leads them to fatally crashing into the ground and killing everyone on board, which I believe there were 7 people on board total. So this tragic example is essentially a good example of how weight imbalance can affect the aircraft performance. And obviously, yeah, worst case scenario lead to fatal situations like that, fatal accidents. But in that scenario, what you saw is that 747, it was a cargo plane that unfortunately did not have the cargo properly attached, and the cargo shifted all the way back to the very rear tail end of the aircraft, which caused it to just stay in that nose up position. They were not able to lower the nose, causing them to just continuously stall and slow down and then just fall flat to the ground, unfortunately. Really, really tragic accident. But it goes to show you, and we'll get more in depth on essentially the effects of center of gravity shifting back and of course forward and so forth. But it's an example of why weight imbalance is very important. So again, overview, right? We'll talk about the effects of weight imbalance on aircraft performance. We'll learn how to compute weight imbalance in a little example. And we'll also talk about, on the next slide, weight imbalance terms, which are useful to know, to kind of familiarize yourself with and write down to study for later use. But let's go ahead and start. So we got our basic weight imbalance terminology, starting with a very important one, which is known as the reference datum. The reference datum is essentially an imaginary line where all the measurements are taken along the aircraft. So this is determined by the manufacturer. The manufacturer, let's say in this example right here to the image to the right, they decided that they were going to take all measurements from the tip of the spinner. And so that's how they would essentially calculate things. And so the distance from that reference datum is what's called an arm. And so that's the horizontal distance from the reference datum line, which is useful in order to calculate the center of gravity. And then, of course, the distance from the reference datum can determine the specific location along the aircraft, which is known as a station. And as you see in this bottom right example, there's various stations along the aircraft. You have, for example, the pilot passenger station, a rear passenger, maybe 2 different baggage compartment stations, and also like a fuel station, which isn't shown on here, but something that would be, of course, on your pilot operating handbook that you can check when you're calculating. And so when we're calculating weight and balance, we have something that's called a moment. And the moment is essentially the weight of, for example, like let's say the pilot and passenger, or some specific maybe baggage in the baggage compartment, times the distance from that datum, so which is the arm, right? So weight times the arm gives us the momentum that weight is felt along the aircraft, essentially. And so that will eventually lead us to being able to calculate our center of gravity, which you've probably familiarized yourself with and heard this term back in maybe physics in high school when you were studying. But the center of gravity is that point along the aircraft which essentially the weight is concentrated along the aircraft. So if you think about it, imagine like you try to spin the aircraft in air on a string, and if it were balanced, essentially that center of gravity, that's where the center of gravity would be, like in this example right here, directly balanced. And there's limitations to it, which we called CG limits. So there's a limitation to how forward that center of gravity can be. Say it's like really far forward. And then of course limitations to how back and what's known as aft the center of gravity can be during flight. And as you saw in that example with the case study, the center of gravity exceeded the aft limits, which caused it to get into that stall and fall. We'll talk a little bit more about that. So write these terms down. It takes some time to write it down. Pause the video. And it's important that you know these terms. It's going to be something that you might be asked on your written exam, of course, and just good to know overall, because this might be asked on your check ride when the DPE gives you a weight and balance example. All right, so some other terminology that is important to know, starting with basic empty weight. The basic empty weight is essentially the weight of the aircraft with the equipment that's installed in the aircraft and any unusable fuel, as well as full fluids, but fluids that are such as oil or, for example, hydraulic fluid that can be found in landing gear. So it does not contain usable fuel that would be actually used in flight. And then, of course, that's the difference between unusable fuel that can't be used because it contains contaminants, it's stuck in the fuel lines, and usable fuel that is actually located in the tanks that are going to be used for flight. Okay. Then you have your max takeoff and your max landing weights. These are essentially the greatest weight that is allowed, published by the manufacturer for that aircraft for takeoff or for landing. Now, this is something that you can check in the Pilot Operating Handbook in Section 2, Limitations. And really, I think for most trainer aircraft, now don't quote me on this, but for most trainer aircraft such as the Archer and the Cessna, the takeoff and landing, max takeoff and landing weights, I should say, are exactly the same. But it's always good for you to check that Section 2 limitations to be sure you understand the max takeoff and max landing. But then you also have your max ramp weight, which is essentially the max weight that is permitted that the aircraft's permitted, and this includes the passengers, right? The any kind of baggage, of course, all fuel, and this is only for taxiing purposes. That's it. So you can't take off, you can't land with this kind of weight. You know, this weight is only for taxi. And you have maximum zero fuel weight. This is the maximum allowable weight that is essentially excludes usable fuel. So essentially everything else, passengers, baggage, anything, right? But no fuel included. And then you have the payload, which is the weight of the occupants, as I mentioned, the cargo and any kind of baggage. And if you want to find what's known as the useful load, that's where you would take your basic empty weight of the aircraft and you would subtract that by your maximum allowable gross weight, let's say for the ramp weight or for takeoff, to find that useful load. I usually am more conservative and do for takeoff because obviously if you make sure that you don't load too much and then you're kind of closer to the max ramp weight and now you got to burn off a bunch of fuel. Okay. And then there's some standard weights per gallon, of course, in aviation that's useful to know. So for example, aviation gas, such as 100 low lead, weighs 6 pounds per gallon. And so this is going to be something useful for you to know when you're calculating the weight and balance, because fuel is going to be something that you calculate. And depending on how many gallons of fuel, right, you're going to need to multiply that by 6 per each gallon, right, to get the amount of pounds in fuel that you're having for the flight. And of course, jet fuel is a little bit more heavier. Oil is heavier, almost 8 pounds, 7.5. And water, is going to be heavier. but it's the most important one really is kind of the gas and the oil for you to kind of remember. So 6 pounds and oil 7.5. So just kind of, again, write these down, memorize these, and this could be something that you could be asked by the DPE, and of course asked on a stage check or on your written exam. All right, so as I mentioned, the effects of weight imbalance really it really affects our performance of the aircraft, right? Depending on how the weight imbalance of the aircraft is, right? So for example, heavier aircraft are going to have reduced rates and angle of climb because they're much heavier. They're gonna climb at less feet per minute, right? It requires much more thrust, much more force to climb at that same rate of climb, feet per minute, in comparison to, of course, lighter aircraft. Added engine wear due to overheating, and this can happen especially on single engine because when you're climbing, and especially during the summer or high density altitudes, when you're climbing, what can happen is the engines can kind of start to, on air-cooled aircraft, the air entering the engines can kind of start to reduce, and then it starts to kind of heat up, which is why you might be told to kind of reduce the nose and allow air to kind of enter the engine compartment, right, the cowling. Lower the maximum altitude, so you're not going to be able to climb to the same max altitude, whereas with a lighter aircraft you will. Slower cruising speed, right? The heavier you are, the more thrust you're going to need to achieve the same speed that you would at a lighter lighter weight of aircraft. So for example, let's say one day, your aircraft is at 3,500 pounds, and you're only able to cruise at maybe 120 knots, but then the next day you're at 3,400 pounds, so 100 pounds less, and now you're able to cruise at 125 knots. So that's how it could kind of be different. Reduced range. This is essentially calculated in distance, right? So nautical miles. With heavier aircraft, there's going to be increased fuel consumption, so that's going to increase the amount of distance that you can travel. Reduced maneuverability. With heavier aircraft, right, they have greater load factor limits, and of course you're not going to be able to maneuver as much with them. And then higher stalling speeds. This kind of goes back to maybe, for example, if you take the example of steep turns, when you're turning, you require much more lift. Well, heavier aircraft even requires much more lift to be able to hold altitude, and that means higher angle of attack. So what does that mean? Higher stalling speed, right? So that just means that instead of stalling at that original speed of maybe, let's say, I don't know, when it's 3,400 pounds, you'd stall maybe at like 95 knots or something, or this is just hypothetical, of course. And then at a much heavier weight, like 3,000, maybe 600 pounds, you would stall at, I don't know, 110 knots, right? So higher stalling speed is going to be something that you can encounter. You're going to need to, of course, come in at a much higher speed, and you're going to have a longer landing rollout. So this is something to make sure that you have that distance and enough runway, of course, for the airfield that you're landing on. Another thing that could happen is weather, depending on where the center of gravity is located, right? It could put too much weight on the nose wheel of the aircraft, or if tail wheel, on the tail wheel of the aircraft. And of course, this can always overstress the aircraft structure, right? Aircraft are designed with certain tolerances, and the heavier the aircraft, the more stress is going to be put on the structure of the aircraft over time. So that's the example of how heavier aircraft will have an effect on weight imbalance and performance overall. But now we need to talk about the overall stability and controllability of the aircraft. And so first, we need to know what stability is, right? So stability is essentially that that quality of the aircraft to return back to its original state, which is we would think of as equilibrium. And then controllability is, how the plane responds to your pilot input. So, whether you're deflecting ailerons or you're putting in maybe some yoke, to climb up, or pitch down, right? And then, of course, maneuverability. This is essentially how the aircraft is able to withstand those stresses with change in direction of the aircraft. So the more forward the center of gravity is, essentially the more heavier the nose is. And this requires things such as more tail downforce to maintain level flight. It also leads to greater longitudinal stability, and that leads to a greater angle of attack needed in order to maintain that level flight. So if you think about it, right, you have your nose, it's kind of pointing down and you want to cruise, but in order to kind of keep that altitude, you need to have a little bit of back pressure added. So that's increasing your angle of attack. That increases drag, and that overall increases your stalling speed now because you're creating more drag. So with an aft CG, this means that you have a heavier tail, and this is where there's less tail downforce in order to maintain level flight. And then, of course, poor longitudinal stability because the center of gravity is actually closer to the horizontal stabilizer, or stabilator if the elevator and the horizontal stabilizer are connected. And then, of course, this will lower your stall speed because the center of gravity is already kind of more forward back, so you don't need to, you're not increasing your angle of attack like you would in a more forward center of gravity in order to keep level flight. You're already kind of, if anything, you might have to actually push down a little bit or add some nose trim down to kind of keep level flight. Otherwise, it'll pitch up, right? So just kind of keep this in mind when it comes to forward center of gravity. Again, greater tail downforce on the elevator or the horizontal stabilizer. Greater longitudinal stability, because the aircraft, what's going to happen is if it stalls, for example, it's going to want to fall back down. The nose is going to want to fall back down. And then angle of attack is greater, causing more drag, leading to a higher stalling speed. So higher stalling speed with forward center of gravity. Aft CG, again, less tail downforce because that center of gravity is closer. This example is closer to the stabilator. And then poor longitudinal stability because, as you saw in that example, because that center of gravity is closer to the elevator, now it's harder to push the nose down if you stall. So that's why there's the longitudinal stability is more worsened, and lower stall speed because you don't have that extra back pressure that you would with a forward CG. So you're not creating as much drag essentially. So you have a lower angle of attack in comparison to a forward CG. So just write these down, memorize these, and make sure you're ready to move on with me. And when it comes to weight and balance, right, it's very important that we always comply with the operating limitations, making sure that we're using up-to-date current weight and balance information. That includes the basic empty weight, but also for every single flight as a result of 91103, which is the pre-flight, that's that NW craft, right? Always take into consideration the weight and balance for each flight. It could be different. It's going to be different, especially because you might be with somebody flying with somebody another day. You might be flying with less fuel, right? Things of that nature that are very important to consider. All right, so now we've gotten to a very important part, and that's how we actually calculate weight and balance. So there's a couple of steps, and we'll kind of go in order on how to go about it. So number one, you want to find the basic empty weight of that aircraft. This is something that you can find in the pilot's operating handbook or the airplane flying manual, of course, of that aircraft. And it's specific to the aircraft because every aircraft's basic empty weight might be different. Some aircraft might have optional equipment that's installed and so forth. So it's very important that, of course, you make sure you have the basic empty weight for that aircraft. The arms, so this is essentially the distances. As you can see in this example, the arms are, of course, each station calculated in inches from that reference datum. And then, of course, the moments, which is, as we mentioned, the weight multiplied by the arm, so multiplied by that station, which is going to be, of course, in hundreds of thousands or tens of thousands. And this is something that you'll do for each station, essentially. So weight times arm equals moment. You'll calculate that for each station. And then, of course, you'll take, at the very end, you'll add up all the total weights, like in this example. And then, of course, all your total moments that you calculate. And that gives you your... and that is going to be something that you'll need to calculate your center of gravity. So you'll take your total moments and divide that by your total weights. So as you can see right here, this guy, he got all his weights for each station. Right? He even got his fuel burn, the amount of fuel burn he's going to do for his run-up, taxi and run-up, and then, of course, for the trip and so forth. He deducted it, and at the end, he got his total weight. And what he did is he took each weight for each station, multiplied that by each arm, got the moments for each station, and he just added them all up, and then, of course, subtract, and then, of course, took into consideration the amount of fuel he would burn, and at the end, he got his total moments. Divided those two, and that gave him a center of gravity of 88.7 in that example. And we're going to do one on the next slide, but this is just kind of to show you how this guy calculated it. Of course, you would do this with your flight instructor on the first lesson, in person, to make sure that you understand how to calculate it. But we'll go through an example. And something else we'll also be talking about is weight shifting. This is something that could be, of course, this could be asked on the written exams or even on the check rides. They can have you, they give you like a scenario, right, where you're adding weight or removing it, or if you're just shifting weight from a different station to another station. So we'll talk about that 2 slides from now, but let's go ahead and do this example. So, all right, in this example, right, we kind of have everything in place, but we take our basic empty weight, which is 2100, and we take the arm for that basic empty weight, which is also going to be given to you with the weight, which is 78.3. Multiply those two, and you get 164,430 for the basic empty weight. And you go from each station to each station. So the front seat, in this example, 340, multiply that by 85, that gives us 28,900. Then the back seat, 350 pounds, and then multiplied by 121 to give us 42,350, and so on. So you get the idea. We're just taking all our weights for each station, even for fuel, multiplying it by the arm that's located, and these arms are located in the pilot operating handbook. The pilot's, the POH, I said that correctly. I'm tripping myself out here. And of course, you take your total moments, and you divide total moments divided by your total weight to give you the center of gravity. And you would essentially find in the section of the POH where there's a chart to make sure that your center of gravity is located within the forward and aft limits. This is something that you can do with your instructor to make sure, or you can check in your POH to make sure that it is within that center of gravity envelope. All right, weight shift example. All right, so let's say we're flying, right, and we're using the same example. We already did our weight and balance calculation, but we're going to have to add 45 pounds because we have somebody named Susie on our flight, and she forgot her makeup kit. Apparently her makeup kit, it weighs 45 pounds. Don't ask me why. Women and their makeup, right? So how do we go about this? Well, we're adding weight. So this is where we'd have to use this formula. So essentially, it's just a little bit of cross multiplication that you kind of learned back in elementary. And so you would take the 45 pounds of added weight, right here, 45, and then you would add your 45 pounds to your previous weight. So we got, in this example, 3,320 plus the 45 pounds that we're going to add, and that's going to give us our new total weight that we put below the added weight. And this CG and this delta sign, that just means the change in center of gravity, which we're calculating. So we'll solve for this. But we need to also find the station change and minus the old center of gravity. So we take the center of gravity that we calculated, 84.3, and we subtract it by the station. So let's say Susie's going to put that 45-pound makeup kit in the baggage compartment. And so we know this arm, this station, is 150 inches from the reference datum. So we're going to subtract 150 minus 84.3 to give us our the difference in the inches of change, in the arm change, essentially. All right, so once we do that, we come to the conclusion that it's 65.7 inches of a change. We multiply that. We'll do some cross multiplication. 45 times 65.7. That gives us 2,956.5. And we divide that by our new total weight of 3,365 to get a new center of gravity change of 0.87. So not much. But this tells us the change, so we need to make sure that it's still within the tolerances. So how do we do that? Well, because we're adding, and especially since we're adding it to a more rear compartment, we're going to add the 0.87 center of gravity change to our previous center of gravity of 84.3, and we get a new center of gravity of 85.17 inches. And of course, we'd go to the center of gravity chart to make sure that it's within the CG envelope, that it's not anywhere forward of the limits or it's not anywhere after the limits, and so forth. Now, unfortunately, Susie says, you know what, I actually need my makeup kit because I'm going to need to put on makeup in mid-flight. And so she needs her bag to be with her in the back seat because she's going to be here in the back seat as an occupant, right? And we're in the front seat. So we already added weight, so we don't really have to do anything in regards to adding or removing weight, but we need to figure out the amount of weight that's being shifted to, again, see if it's within the center of gravity tolerances. So this is where we would use this formula. Weight shifted over the total weight, and then the change in center of gravity over the weight shift distance. So it's very similar to the one we just previously did. So we come here, we put, again, 45 pounds of weight being shifted because it's that makeup kit that weighs 45 pounds that we're shifting over the total weight, which is, of course, the new total weight that we already calculated for, 3,365. And then on the other end, we're going from the baggage station, which has an arm of 150 inches, subtract that to the new station that we're moving it to, the back seat, of 121 inches. So that gives us, if we subtract the two, that gives us 29-inch difference. So you see here, 45 times 29, because we cross multiply. That gives us 1,305. And now again, as in the previous example, we'll divide that by our total weight. And that gives us a 0.39 change in center of gravity. Now, we're going to subtract because we are moving it more up forward of the along the aircraft, I should say. So 0.39 minus the new center of gravity that we calculated, 85.17, gives us a new center of gravity of 84.78. And again, we check the chart, see, hey, are we still within the CG envelope tolerances? And if we are, we're good to go. Susie can put on her makeup, all dandy, all good, right? So there you go. That's weight shift in a nutshell. And of course, you could take this example, you can pause it and kind of write this example down to study it. Definitely, I recommend, of course, writing down these two formulas to kind of study them and practice a couple of questions, because this is definitely something that you will be asked at least for sure on the written exam. So this is definitely good for you to know, and it could be asked on the check ride. All right, so overall, just kind of recap and discuss, right? We talked about why weight imbalance and why weight imbalance is important, and that's because it affects our performance, right? We want to make sure that it's within the tolerances of the aircraft, right? We don't want to make sure that it's too far forward, it's too far aft, and if it is, that it's within those tolerances, that we're not exceeding what the aircraft is essentially tolerated for, right? We know what center of gravity is. That's the concentration of weight along the aircraft, right? Again, think of the way the aircraft being suspended. It's able to stay suspended and balanced. And then, of course, we'll ask ourselves, well, what happens when center of gravity is too far aft? As we saw in that example, if it's very far aft, you can lead to that fatal accident where you are not able to recover from a stall. But again, it leads to, of course, decreased lateral stability, but it leads to an increase in cruise speed, which leads to, of course, a decrease in fuel consumption, and, of course, increase in range and so forth. And we already talked about how to calculate the center of gravity and so forth, so you can always rewind and kind of go back, but this is the recap and discussion, and these are the sources: Pilot Operating Handbook, Aeronautical Knowledge, Chapter 10, really good on weight and balance, gives good examples and so forth. And then you can always read the Aircraft Weight and Balance Handbook. There's some good chapters in there that, of course, are useful to study, especially before you're written and before your check ride. So overall, that's weight and balance in a nutshell, and thanks for watching.